Okay, so as promised, I wanted to do an example of finding the sixth roots of unity. In class, we found the fourth roots of unity, so this is just another example of how we would use Euler's formula or de Moivre's theorem to compute roots of unity. So just as a reminder, roots of unity, so the nth root of unity is going to be e to the 2 pi I k over n for k equals 0, 1, 2, all the way to n minus 1. And we stop at n minus 1 because if we went on to n, if we went on to let k equal n, we would just repeat all the same roots again. Okay, so for the sixth roots of unity, so in our case, n equals 6, because we're finding the sixth roots. So we would have, we're trying to compute 1 to the 1/6, which is going to be e to the 2 pi I k over 6, where k goes from 0, 1, 2, 3, 4, and ends at 5. Okay, because that's n minus 1. N is 6, 5 is n minus 1. Okay. I'm going to actually draw the roots of unity also in the complex plane to give you an idea of where they are in the plane. So remember, this is the real axis on the horizontal, and this is the imaginary axis. Okay, and we just start with k equals 0 and go all the way to 5. So we'll start with k equals 0. So in this case, we have just plugging it in to this formula here, we get e to the 2 pi I times 0 over 6. This is going to be e to the 0. Any number to the 0th power is just 1. So in the complex plane, I'm just going to plot the point 1. Okay, and that lies on the real axis because 1 is a real number. Okay, so next we're going to go on to k equals 1. So for k equals 1, we have e to the 2 pi I times 1, because that's k, over 6, which is n in this case. All right. If I simplify that exponent, I'll get e to the pi times I over 3. If I plug this into Euler's formula, this would give me cosine pi over 3 plus I times sine of pi over 3. And I just do that so that I can have a sense of where this is going to be in the complex plane. You could also think about it as this giving you the angle where the number would lie in the complex plane. The modulus of this complex number is 1. So it's going to be a distance of 1 from the origin at an angle of pi over 3. So an angle of pi over 3 would be somewhere in this direction, maybe, roughly. Okay? And we can see that that's where we're going to get, that's where we're going to end up with our real and imaginary components. So cosine of pi over 3 is 1/2 plus I times sine of pi over 3, which is root 3 over 2. Okay, and then if we go to that point, if we go 1/2 in the positive horizontal direction and root 3 over 2 in the positive vertical direction, we would end up at this point here. So this is the point 1/2 plus I root 3 over 2. Okay. Next we're going to compute k equals 2. So I'll do that right here. So I have e to the 2 pi I times k, in this case k is 2, so times 2 over 6. This is going to simplify to e to the 2 pi I over 3. So we could think about this as being at the angle of 2 pi over 3, which is somewhere along, maybe roughly in that direction. So that's measuring 2 pi over 3 in that direction. Or we can use Euler's formula to write down that this is equal to cosine 2 pi over 3 plus I times sine of 2 pi over 3. Remember with Euler's formula, whatever is next to the I, so everything except the I, is what goes into the sine and the cosine arguments. So this is going to give me cosine of 2 pi over 3 is negative a half plus I times sine of 2 pi over 3, which is root 3 over 2. And again, that's going to land me somewhere around here. This is minus 1/2 plus I times root 3 over 2. All right, so we're going to go on to computing k equals 3 e to the 2 pi I times 3 over 6. This is going to be e to the pi I. And using that same argument with the angle in this case is pi, and that lands us directly on the other side of the real axis. So we're going to do, we could also plug this into Euler's formula to get cosine pi plus I sine pi. That tells us explicitly the real and imaginary parts, which is a good indication of where it's going to be on the complex plane. So cosine of pi is negative 1. Sine of pi is 0, so this is just going to be negative 1, which is going to land us somewhere around here. So that's negative 1. Okay, so next we're going to compute for k equals 4. So I have e to the 2 pi I times 4 over 6. This is going to simplify to e to the 4 pi I over 3, which again, we could go 4 pi over 3 radians, or we can write down the Euler's formula for this, 4 pi over 3 plus I times sine 4 pi over 3. This is going to give us minus a half, minus root 3 over 2 times I. So 4 pi over 3 is somewhere along here, so that point's going to be somewhere maybe a little bit closer here. So we've got minus a half minus root 3 over 2I. And finally, we're going to compute the value for k equals 5. So we get e to the 2 pi I times 5 over 6. This will simplify to e to the 5 pi I over 3. This is going to be cosine 5 pi over 3 plus I times sine 5 pi over 3, which is going to give us 1/2 minus root 3 over 2I. And if we plot this in the complex plane, that's going to be, we're going to go 1/2 in the positive horizontal direction, and then we go negative root 3 over 2 in the vertical direction. So that's going to put us roughly here. And again, that's at the angle 5 pi over 3. So this is 1/2 minus root 3 over 2 times I. And these are the sixth roots of unity. Notice there are 6 of them. If we had gone on to compute for k equals 6, we would actually get 1 again. So we don't need to do that. And then I just want to point out very quickly that this forms a regular hexagon. So if I connect the dots here, I get a regular hexagon in the complex plane that lie, and all the points are evenly distributed around the unit circle. So I hope this helps clear things up. If you have any questions, always stop by office hours or send me an email and I'd be happy to help.